Hi, and welcome back to the next video series on waves and light. Today we're going to be discussing critical angle and total internal reflection. Total internal reflection is the third refractive law that we had mentioned at the beginning of the refraction series. To remind you, the greater the end, the greater the bend, and the refraction Snell's law, low to high, slow down and bend towards the normal. There is a special condition. When the incident angle is at a certain angle, it causes the refracted ray to bend exactly at 90 degrees to the normal. And after this angle, you have internal reflection. Here's a little mnemonic we're going to be using. When theta I is theta C, theta R is 90 degrees. Okay, let's take a look at it for real. Here I have the PhET simulation again. And this time I've reversed which side has the higher index of refraction. I have the higher index of refraction in this purple region. I made it 1.51 for glass, and I have air as the N2. Now I turned on the laser and you can see that the beam is shooting down the normal, so there is no refraction. But when I begin to offset this beam a few degrees from the normal, say 20 degrees, you can see that the beam goes across the boundary and refracts. Now, if you remember the rule, low to high, slow down, bend towards the normal, you should also remember the reversibility of that rule, high to low, speed up, and bend away. So this ray of light actually bends back and away from the normal. Well, there's another point that we had been talking about, and very briefly at that there is this very faint reflected line. This very faint reflection of the incident ray is the equal angle to the incident angle itself. Now there's a point at which I can continue to adjust this angle of incidence, and the ray that refracts is getting closer and closer to the boundary. And at the same time, this ray, which is reflected, is also getting closer and closer to the boundary until at a certain moment right here, the refracted ray completely disappears, and then it is all reflection off the surface. So even though that these are two translucent materials, there is a critical angle, hence the name of the lesson, at which the ray can no longer pass through the boundary and will completely and totally reflect. Let's take a look at that in a diagram. Here I have a type of fish tank setup where below this horizontal line, which is the water line, I have a light bulb placed, say, at the bottom of the tank, and this above the line is just the air. If I was to draw 1, 2, 3, 4, 5 different rays of light coming from this bulb, I could examine each one of them independently. For this first ray, it hits the normal at 0 degrees and is at the surface 90 degrees. So it just passes straight through. Now if I examine this ray here, it meets the normal line, which is this dashed line, at some theta 1. And because you're going from high n to low n, you speed up and you bend away from the normal. This is a typical refraction that you would be expecting. The same bulb is emanating a light ray somewhere to this place in the water. And again, here's the normal line, and this is the incident angle. But the incident angle here is much bigger than the incident angle of the first ray. So it refracts and bends away from the normal more than the first ray did. Now this continues as a process as I get further and further away from the original ray, which hit at 0 degrees on the normal. Eventually, there is a place called the critical angle. This refracted ray bends exactly at 90 degrees to the normal. So the incident angle becomes the critical angle when the refracted angle is 90. Let's remind ourselves of that little rule we had before. When theta I is theta C, theta R is 90 degrees. And here it is again so you can see it. When theta I is theta C, theta R is 90 degrees. Now, any ray that strikes the surface and meets the normal at an angle greater than the critical angle is now internally reflected. and the reflection angle is equal to the incident angle. At the point of the critical angle, you have a 90-degree refraction, but after the critical angle, you have an angle of reflection equal to the incident angle. Let's take a look at a problem. Here I have a block of lucite and air, and I have a ray of light exiting lucite into the air, and the question is, find the critical angle. So we know from Snell's law, n1 sine theta 1 equals n2 sine theta 2. But because we're dealing with the critical angle, we need to have a ray that has a 90-degree refraction. When theta I is theta c, the incident angle is the critical angle, theta r is 90. So when I plug this into the Snell's law formula, going from lucite into air, the n1 of lucite is 1.5 times the sine of the critical angle. That's the unknown we're going to solve for. That is equal to n2, which happens to be air. The value is 1 times the sine of 90. It has to be 90 because at the critical angle, theta 2 is the refracted angle of 90 degrees. When I do the mathematics, 1.5 sine theta c equals 1 times the sine of 90. The sine of 90 is 1. So I then solve, dividing by 1.5, taking the arc sine, and I get 41.8 degrees. Therefore, the critical angle in an air lucite boundary is 41.8 degrees. Any angle less than 41.8 degrees will cause refraction. Any angle greater than 41.8 degrees will cause total internal reflection. Let me show you. For any angle of incidence less than 41.8 degrees, like this red line, you will simply see a refraction. And since you're going from high to low index of refraction, you're going to bend away from the normal. But any angle of incidence greater than 41.8 degrees, like you see here, this red arrow is beyond the 41.8 degrees, you will have total internal reflection, like you see on this side. So the angle between the normal and the incident ray is equal to the angle between the normal and the reflected ray. And that concludes our explanation of the critical angle and total internal reflection. Thank you for watching. I hope you enjoyed this video, and we'll see you in the next video.